Welcome to week 19 of Pure Maths 3 Maintenance Team. Hope you're going well. We've got a lot to do today. Starting off as usual with Algebra. And we have the polynomial of 4x cubed plus ax plus 2. A is a constant, it's denoted by px, and we know that 2x plus 1 is a factor of px, so we've got to find the value of a. Well, if it's a factor, that means that p negative 1/2 should be equal to 0. Okay, it's a root. Minus 1/2 is a root. So what we do then is we go 4 times minus 1/2 cubed plus a times minus 1/2, so minus 1/2 a plus 2 equals 0. And then in the next line, what we have here is negative 1/2 for that first term, minus 1/2 a plus 2 equals 0. And what do we see? And then we can go negative 1, or we can go 1/2 a, because we can move the a across the other side, equals 3/2. And so a equals 3. That's it. When a has this value, factorize. Okay, there's a couple of ways that we could do this. So if this is a factor, we can multiply it by something x cubed plus something x squared plus something x plus a constant, and we can kind of work it out logically. So I'm thinking, oh sorry, actually we don't have an x cubed term. I've gone OTT. We've got x squared plus x plus a constant. Now the constant to me looks like it's got to be 2, otherwise there's no way we can get this. So I think it should be a 2 there. And obviously if we're going to get a 4x cubed, we need a 2 here. And then we just got to work out what is going to be in here. Okay, so now you can do that by thinking about how we're going to get our x squared terms. So our x squared terms must add to 0, because you can see up in the original equation that there is no x squared term. And the way you make an x squared term is this times this, and the only other way is this times that. So you can see that we must therefore have a minus x. So at this point I'm thinking we can go minus x. Now if you can't do it that way, that's fine. The other way you can do it is to use long division. So it's not perhaps as elegant a method, but hey, whoops, hang on, what am I doing? But you can, get the right answer, which at the end of the day is all we're interested in for this. We don't have any x squared, so 0 x squared, and then we go plus. We know that a is 3, so 3x. And then we've got plus 2 at the end, okay? And you can see that, well, we need a 2x squared to get this first one, so we get 2x squared cubed plus 2x squared, and we subtract those from each other. We're left with negative 2x squared. That's right, isn't it? Yep. And then we bring down this 3x, so plus 3x. Now we're going to go into that, so we need a minus 1, I think. Minus x. Yep. So we get minus 2x squared minus x here, and we subtract that away, and we're left with 4x. You're going to bring down this plus 2 here, and now you go 2x plus 1 into that, well, you can see easily that's just going to be plus 2. So we get 4x plus 2. Subtract that out, no remainder. So there we go. This is our answer then, isn't it? Oakley dokley, moving on to the logs question. Now I noticed I've just marked your mid-years, so I'm doing this probably half a term before you need to watch it. And a lot of you have been trying to remove the logs straight away. So you would be doing something like this. Okay, but you can't do that, okay? You must first of all get everything on one side. So you've got log something, like this, equals log something on the other side. Now we can use our log rules. So this is log 4x squared. We're using two log rules there, aren't we? So it's ln x squared plus ln 4, and when we're plussing ln, we can multiply those and make it just ln 4x squared. Now we can get rid of the logs, okay? At this point we can. So I get this, and then I'll probably just bring everything over to the right hand side. So get 3x squared minus 4. Well, maybe I should have just left that. Yeah, 3x squared equals 4. So x squared equals 4/3. And so x equals plus or minus the square root of 4/3. Or x equals plus or minus 2 over square root 3, just simplifying it. Now, when you're thinking about logs, remember we can't put in a negative number. Ln is not defined for negative values of x. Ln x is not defined for negative values of x. So in this case, we'll say x, we can get rid of that one. So we'll say x equals 2 over square root 3, and that would suffice. Okie dokie, moving on to the trigonometry question. Now, we've got to turn this into a quadratic equation in tan. And hopefully you can see that we have the addition rule is going to be used here. So, hopefully we've got enough space here. So my first step is to turn tan theta plus 45 into tan theta plus tan 45 all over 1 minus tan theta tan 45. Then I'm going to go minus 2, and I'm just going to do a big square bracket, and I'm going to do the same thing. I'm going to use the addition rule here with the theta minus 45, and for that, remember we've got our formula sheet. So this is tan theta minus tan 45 all over 1 plus tan theta tan 45. Close the bracket, equals 4. Okay, so we did our first step, probably got some method mark there, and we're on our way. Now, what I'm going to do at this point is I'm going to get rid of my tan 45s, because I know that tan 45 is 1. So my next line is going to be tan theta plus 1 all over 1 minus tan theta. Then I'm going to expand the bracket, so I'll get minus 2 tan theta minus 2 all over 1 plus tan theta equals 4. Alright, I'm going to cross multiply so that I can get one denominator. So I'm going to get tan theta plus 1 into 1 plus tan theta. So it's the same thing, we're squaring it. Minus, we'll go 2 tan theta minus 2 times by 1 minus tan theta. All over our new denominator, which when we expand it would be 1 minus tan squared theta. Okay. Now at this point, I can, equals 4. And at this point, I'm going to expand my brackets on my left-hand side. So I get tan squared theta plus 2 tan theta plus 1 minus, and I'll put this in a bracket so I don't make any silly errors. So I'm going to get 2 tan theta minus 2 tan squared theta minus 2 plus 2 tan theta. And then I'll say equals to 4 bracket 1 minus tan squared theta. Now, I'm going to gather my like terms. So this is going to affect everything inside this bracket here, isn't it? So let's just focus on the old tan squareds. So I get minus 2 tan squared. So it's positive 2 tan squared. So we get 3 tan squared theta. Now we're going to look at inside the brackets. We've got 4 tan theta, but we're because we've got 2 tan theta plus 2 tan theta, but we've got a minus, so it'll become minus 4 tan theta. And I've got positive 2 tan theta outside, so it should be minus 2 tan theta. Now let's look at our constants, non-theta terms. So we've got inside the bracket, we've got minus 2, which becomes positive 2 when we apply the negative from the outside. So we get 1 plus 2, which is 3. So plus 3, and this should equal 4 minus 4 tan squared theta. I'm going to bring our work up to here now. Okay, bring everything across to one side. So I'm getting 7 tan squared theta minus 2 tan theta minus 1 equals 0. Now at this point I'm just going to apply the quadratic formula. So tan theta equals minus 2 plus or minus the square root of minus 2 squared minus 4 times 7 times minus 1 all over 2 times 7. Now we get tan theta equals 2 plus or minus square root 32 over 14, and so we get theta equals the inverse tan of that, so 28.7 degrees is one of my results. And when I use the second one, the 2 minus square root 32 all over 14, I get negative 14.6, which of course is not in the range, so I can ignore that one. And then I'm looking for one in this range, so I just add 180 because it's a tan graph. That's the period of a tan graph, so 165.4, and there we go, that one's done. Alright, moving right along. This is a long one today. Feels like it anyway, or maybe I'm tired. We've got differentiation. What have we got here? Oh, seriously. Alright, find dy dx in terms of x and y. So you can see on the left-hand side of this we've got a product rule, u times v. And when you are differentiating that, dy dx of course is equal to u dv dx plus v du dx. Okay, this is a v and this is a u, just be careful there. Alright, so how are we going to write this? So that first side I'm going to go sine y times, and I'm ddx of ln x plus, now I'm going to do v, which is ln x, plus oh sorry, not ln x, plus, yeah, ln x, and then I'm going to apply ddx to sine y. I think I should probably have that after them, shouldn't I? never mind. I'm on track now. Okay, and then equals x by d dx minus 2 sine y d dx. Okay. Now, in the next line, when we're applying d dx to ln x, we should get 1 over x. So I think we get 1 over x sine y. And then for the next one, plus ln x. And then we're going to apply, we're going to go times sine y times d... what are we going to do? Yeah, dy dx by d dy. Okay, and then I can differentiate that with respect to sine y. I'll do that in the next line. This becomes 1, this x, and then we're going to do the same thing here. Sine y d dy. I'm doing this out like the slow way, dy dx. Okay. Now next line we could rewrite this as sine y over x plus. Now if we differentiate sine y, we should get cosine y. So we're going to get ln x cosine y and then dy dx equals 1 minus 2, and then that will be cosine y, I think. Cosine y dy dx. Now at this point I'm going to bring I'm going to gather my like terms here. Maybe I'll go over here because I've got a little bit more space. So I will go 1, so I'm going to bring the sine y across to the right hand side. So 1 minus sine y over x, and then I'll bring the negative 2 cosine y across to the ln x. So here's what I'm going to do, factorizing in one go. So I'm going to go dy dx bracket, and I have my ln x cos y plus 2 cos y. And now I'm ready to get things in a better form. So what I might do is on the left hand side I might write it as x minus sine y over x. It's a simpler way of writing it for what I'm going to do my next step. Equals dy dx, and then I've got this ln x cos y plus 2 cos y. Now I can divide both sides to get dy dx. So dy dx should be equal to this left hand side divided by this right hand side. Now when you've got a fraction and you're dividing by like a number on the right hand side, that this bit here is going to end up multiplying with the bottom, with the denominator. Okay, just think about your basic fractions rule. So we get x minus sine y all over x into, oh, we can probably take that cos y out as well, can't we? Yeah, we'll take the cos y out. So x cos y, and then in it we'll have ln x plus 2. And that's probably the simplest way of doing it. So you'll see that moving up. Whoops, why is that? Oh, don't know what happened there. Sorry. Oh, okay, it's going to be like that, is it? But you can see I've moved this cosine y. I've factorized it out. That's what happened here. Okay, so I think that's probably fine there. Oh, hence, the old hence, eh? Hence, find the exact x-coordinate of the point on the curve at which the tangent is parallel to the x-axis. Now, if we are parallel to the x-axis, what does that mean? Parallel to the x-axis. Well, that means that it's got a gradient of 0. So the gradient is 0, which means that your denominator must be 0. So at this point, we're just going to go x minus sine y equals 0. So we can say that x equals sine y. And we want the exact x coordinate. So what can we do? What could I do? I guess I could I could substitute this into the original equation, perhaps? Okay, so maybe if we look at the original equation that's here, perhaps I can substitute this out, because you can see that I've got those sine y's. So maybe we can go, therefore, we'll have x ln x equals x minus 2x. Yeah, that looks good. That looks real good. So we end up with x ln x equals negative x, and so ln x is equal to negative 1, and so x is equal to, what you do here is, here we go, I'll do one more step just to help you. Okay, so from here I'm going to go ln x equals ln e minus 1, and so we'll get x equals e to the minus 1, or x equals 1 over e. Okay, so remember your log rules. This step's an important one. Okay, so that's our differentiation question. Oh, seriously. Okay, this is really long today. Sorry, guys. Some weeks are longer than others. So integration. Okay, we're using substitution. Your favorite, guys. Your favorite. Okay, and this is the substitution that we're using here. So that's what we've got. I'm gonna do this, and then we've got to show that I equals this. Okay, and then hence find the value of I. Alright, let's do it. Okay, so if that's what x is, we're going to go dx d theta should be square root 3, and remember, when you're differentiating tan theta, you get sec squared theta. So sec squared theta it is. And then we can, maybe at this point, we can go, well, that means that dx is equal to square root 3 sec squared theta d theta. Now, the other thing we can do is we can go, x squared equals 3 tan squared theta. Because I've just squared this information here. Now, let us see, what can we get rid of here? Now, the other thing that we should do to get some marks while we're pondering this is, well, if we know what x is, so x, see we've got our limits here, these limits, we want to always get some points for that. So go x equals 0, therefore, our substitution, we're going to have theta, so we just plug it in. So when we plug in x equals 0, we should get tan theta equals 0, so theta equals 0. And then when we get x is equal to 1, so you go 1 over square root 3, go inverse tan on that, and you get pi over 6. Okay, so I've got some method marks there. Now at this point, what have we got? So we've got this. We got 0 here. We got pi over 6. And we got 9 over 3 plus 3 tan squared theta. So I've just replaced, you can see here, this bit here. Woo! Why is it doing that? Okay, we're not working again. Okay, so replace the x squared with this information here of 3 tan squared theta. Okay, so that's all I'm doing there. Okay, and then I've got times, and I'm getting rid of this annoying dx. So remember what dx is equal to here. So, excuse me, I've got square root 3 sec squared theta d theta. That's how I get rid of that. And then what I can do in my next line is I could probably go and factorize that bottom line. So, oh, that should be squared, shouldn't it? So what I can do at this point is I can factorize out 9. Okay, I'll take out that 3, and it's 3 squared. So I make it 9, and then I've got 1 plus tan squared theta. And that's all squared. Alright, and then I've got times square root 3 sec squared theta d theta. Now we're cooking. So we've got 0, pi over 6, and cancel-y, so we end up with 1 over, and then in this bracket here, 1 plus tan squared theta, that's like sec squared theta, and I'm going to swap it over to that form because I can see that I've got this other sec squared theta that I've got to get rid of at some point, times square root 3 sec squared theta times the theta, and then I can cancel. Moving to the next line, you can see I can cancel this and one of those, so I should be left with pi over 6 here, the 0 here, and we're going to have square root 3, which is perfect, over, we'll have a sec squared theta and d theta. Ah, this is fabulous. Equals, so our next line we can take that square root 3 out, then we have our integral sign. Now, something over sec squared theta. Well, remember sec squared theta is 1 over cosine squared theta, so now we've got exactly what we want. We are done. Hallelujah. Alright, there's our answer. We have shown it. Now we're going to find the exact value of I. So all that we need to do now is to integrate. I think. Is that all we need to do? Now, oh, actually, yeah, just thinking about it, I need to turn this into an integratable form. So we're going to use our double angle rule. So remember, cosine 2 theta is equal to 2 cosine square theta minus 1. And so cosine squared theta, I'm just going to do a little bit of a rearrangement here, equals 1 plus cosine 2 theta all over 2. And now we can replace that. So what we're trying to do is we are trying to go square root 3 and then integrate between pi over 6 and 0 of 1 plus cosine 2 theta. I guess it's like 1/2. 1/2. We could probably just take the whole 1/2 thing out, couldn't we, as a factor? But anyway, equals square root 3, and then we're going to have, well, it'll be 1/2 theta plus, and when we integrate this, it'll be 1/2, 1/4, won't it? 1/4 sine 2 theta. That's right, isn't it? I'm just having a mind blank. I think that's right. And we're going to do that between 0 and pi over 6. Okay, now when we do this, we get square root 3, open up our brackets, pi over 12 plus square root 3 over 8 minus, and then in the next bracket is just zeros, isn't it, right? 0, and then toss in the brackets. Now, once we plug all of this in the calculator, I was getting square root 3 pi over 12 plus 3/8. Okay, the old numerical solution of equations. Is this our last page? Oh, good. Good, I feel like I've been going for an hour. Okay, the equation has one positive root. Verify by calculation that this root lies between 1 and 2. Okay, what we can do is we call x to the power of 5 minus 3x cubed plus x squared minus 4. Call it fx. Now, then we go f1 equals. Now, when I plug that in, I get negative 5, 1 minus 3 plus 1 minus 4. Yep. And then if we chuck in a 2, what do we get? 2 to the power of 5, take away 3 squared, cubed, times 2 cubed, plus 2 squared, minus 4, and that gives me 8. And a sign change indicates a root between x equals 1 and x equals 2. And there we go, we're done. Now we've got to show that the calculation can be rearranged into the following form. So we're looking at this. Why is it doing this? I just want to use the highlighter. This. And how do I get to this? Okay, so we've got to think carefully here. What can we do? I reckon... What do I reckon? Okay, I'm going to go x to the power of 5 equals, and I'll just pull everything else across the other side, because it looks kind of like what I need. Minus x squared minus 4. Now, at this point, I could divide everything by x squared. So you can see I'll get x cubed equals, then I get this 3x. Then I'll get minus 1. And then plus... Oh, sorry, that should have been a plus when I moved that across, shouldn't it? Made a mistake there. Plus, and then there'll be 4 over x squared. Okay, you can see where we're going with this. To get x, then we're just going to take the cube root of all of this nonsense. So we get 3x, I guess, plus 4 over x squared to make it in the same order that they've got it. And we are done. Now, an iterative formula based on this arrangement to determine the positive root. All I would do is I would start with 1.5 as my first value. And it says give the result of each iteration to 4dp. So maybe I'll just do this, right? That's my first one. Then I'm going to go x2. Now don't be a Larry like some of you guys in the exam. Read the question. Determine the positive root correct to 2 decimal places, iterations to 4. So the final answer should be 2dp, not 4dp. So x2, now when I used my calculator for this, and hopefully you guys know how to do this on the calculator, a quick refresher, go 1.5000 equals, and then that becomes answer in your calculator, ANS, and then you set up the formula, the iterative formula, with cube root 3 answer plus 4 over answer squared minus 1, and then you go equals for each new term. We've done it enough in class, you should be fine with it, but ask if you get stuck. So I'm getting these. x4, I got 1.7744. x5 equals 1.7751. x6 equals 1.7753, x7 equals 1.7753. I did one more just to make sure. 1.7753 now. We're getting no change at this point. So x equals 1.78 to 2dp, which is what they've asked for. Lastly, but not leastly, we are doing the old partial fractions. Oh, well. So, by inspection, I know that a is equal to 3. This is not black magic or sorcery. It's simply, if I expand out this bottom, I've got x cubed as my highest power. And I'm thinking, how do I get x cubed? 3x cubed divided by x cubed is 3, right? So I know that a is 3 straight away, just by inspection. Okay, now I'm going to work out the rest of this. So, here's what I'd write. I'd go 3x into x squared plus 2, so that's my a value, plus, and then b is just multiplied by my x squared plus 2, plus cx, and I should put this in the bracket, cx plus d into x equals, and then I've got my numerator, 3x cubed plus 6x minus 8. And then we'll say, let's make life easy, let x equals 0. And when we do that, obviously we knock out this one, and we knock out this one. And so we're going to get 2b equals minus 8. And so b equals negative 4. And then, let me see. I'm going to equate the coefficients. So I'm thinking about this value of d. So I've got this times this. And I can see, so this is for x term. You can see over here that we need a positive 6x, and I've already got that here, and there's only two ways of making a making an x term. So d must be equal to 0, and then lastly I will go let x equal 1 and see if we can find out what c is. So if I do that, I'm going to have 3 times 1, which is 3, times 1 squared plus 2, so 3 times. So I should have 9. That's dealing with the first lot, with the a. Then with b, we know it's minus 4 plus negative 4 into 3, which is negative 12, plus, what do we say, 1. So I guess it's just c, isn't it? C equals, and then on the other side I've got 6, 9, 1. Okay, it should all add up to 1. And so we get 9 minus 12, which is negative 3, plus c equals 1. So c should equal to 4. And I guess then we can write it out. So what have we got? We've got 3 plus, what did we say b was? No, it's minus, it's not plus, is it? Minus 4 over x plus 4x over x squared plus 2, and we are done. Alright, well I hope this has been helpful. It's a long one, but good practice for you guys going through these past exam questions as we head into exams. Practice, practice, practice. Alright, take care.